Okay, welcome back everybody. Let's start with the second presentation. Yeah, okay. So who's going to talk first? Okay, here you go.
Thank you. Right. Thanks for having us. We're going to talk about some, can people hear me? Yeah? Great. We're going to talk about some pattern mining, so it's not as new and as cool as the streaming and the deep learning as we just heard before, which was a really nice talk, by the way. Thank you for that. But we're going to talk about maybe a little less known topic, the topic of pattern mining. And who are we? Well, that's me. I'm Rutger. I work at a different company than this one, Informed. It's a company in Utrecht. But Jelte does work here, and we know each other from our studies in Utrecht, and we both did a thesis on pattern mining. So we hope we know a little about this topic. Yeah, we're both data scientists, by the way. So pattern set mining. I hope you have heard of it before, but we'll just go back to the basics at first. Pattern set mining. You have some data, as we usually do, and we want to find some interesting patterns in that. And how can you do that? Well, first some definitions. We have our data set, usually called a transaction database. And it's a database of transactions. Every transaction has items in it. Yeah, and the items are the individual the occurrences of something. So the most used example is a supermarket with supermarket items like bread and tomatoes and beer and diapers. So what makes a pattern interesting? Well, that's a topic of discussion, and there are a lot of papers about that. But the most common choice is to pick the frequent ones. But you can also think about very long patterns or with some kind of value or describing some kind of database really well. But we'll start with the frequent patterns. Well, for this we define some support. And it's a nice formula, but basically what it means is how many of my transactions contain this pattern. So we have a little database here. This has 5 transactions. I've made this myself. And we want to find patterns with a minimum support of 2 in this database. So it has to occur at least 2 times in this database. So we can just look at all the data, the transactions. And if we look closely, we see that beer and diapers occurs 3 times. So 3 out of 5 times, that's our support. And tomatoes and bread, 2 out of 5. Right? That's everybody's still following me? Good. Right. Why diapers and beer? Actually, this is a story that's just told a lot, I guess. Maybe some you know it already, but it's from the start of the pattern mining movement, I guess. They started in America, some big chain like Walmart or something did some pattern mining algorithm on their transaction database. And they found diapers and beer had a high correlation of being sold together. Like correlation, right? There's not a causation like shown here. But this is like something they would have never guessed to ask their data, and they found while using pattern mining. So being a good supermarket, they put one on the one hand of the store, the other item on the other hand. So you have to walk past all the discounts and do some impulse buying while you're at it. So that's one of the cool things of pattern mining. You really find stuff you're not looking for. But like we just did in our small database, we cannot simply count all combinations we have because there are simply too many. We have on the left here graphical representations of how many items you have. So we start this very small example with only 5 items, and then all the possible combinations. So first we have the empty data set, then the 5 items, then we go one level lower, we have the combinations of length 2, then length 3, etc. Why is it shown like this? Well, this exposes a nice structure they have because they're all like link dependent. If you know something about one, you can also say something about the other. And on the right is a very nice graph showing just how many items we have. If you start to increase the number of items, this explodes. It's called a pattern explosion. With only 19 items, you have like 500,000 combinations of item sets you have to count. So we cannot simply go to our database and count each combinations to see if it has the support we want. So for this, two names I will not pronounce because they are difficult. Made an algorithm in 1994 already, and it's called a priori. It's actually quite easy. It's just a few steps, and I will just walk you through it real quick. So we have a new database with our transactions, some transaction IDs, which we will ignore for now, and our items. Oh, by the way, something I should have said before. The order of the items doesn't matter at all in this case. We can just move them around. Think of it like a shopping basket. It doesn't matter at which order and at the counter you pay for them. So how do we start? We count all the singletons, all these single items. How often do they occur in our database? And again, we're looking for support of 2. So we find 1, 2, 3, and 5 occur at least 2 times in our database. We leave out 4 because it only occurs 1 time. And this is our first result set of frequent patterns. Yay. So we go to step 2. We combine these frequent patterns and we count them again. So then we combine 1 with 2, or 1, 2, and 1, 3, 1, 5, etc. And then we only count these patterns. So we do nothing with the 1, 4, etc. So we already reduced our search space quite a bit. And then we find that there are 2 patterns which are not frequent enough and the others are. So we output the others and we combine again. But this time, combining, we only get to 1 new pattern. So we only have to count this one. And we have all our frequent patterns while not searching a whole space. And this is a Spark talk, of course. So this is actually not the algorithm implemented in Spark. In Spark, they have the FP growth algorithm. And this is a bit more efficient. It first scans the database only once and then sorts the items in frequency. Then does another scan and it incrementally builds a kind of tree for which you can easily mine the patterns. It's more efficient, but this gets the idea across really well, I hope. Jelte will later show how you can do it actually. And from these frequent patterns, we can go to our rules. So you probably haven't heard about this from the pattern mining. If you have buy item A, you will also likely to buy item B, or X and Y, I think I used. And we can say it with a certain confidence. And why is this more interesting? Well, because at first we had a correlation between diapers and beer. But we don't know if people who buy diapers also buy beer, or it's the other way around. Or well, just we can add some more information. And the nice thing about this is that it's actually a simple computation from the support of the complete item sets and the smaller item sets. And because they are already, the smaller ones are also already in our result set, we already have this support. So we do not need to scan the database at all. We can just go back to our small example to show this. So we split each pattern in a left-hand side and a right-hand side. So we only had patterns of length 2, so it's quite easy. For example, beer and diapers, left beer leads to buying diapers. The support we computed before, and it's still the same, of course. But then we can go to the confidence, and then we look for how many times do these items combined occur in our database compared to how many times does only beer happen in our database. Turns out there's a perfect correlation, I guess, so they always happen together, so it's not that interesting. But our second example is the tomatoes and bread one. Tomatoes and bread happened 2 times, but tomatoes on its own is 3 times. So it has a confidence of 66%, but the other way around, it's 1%. So now we can say people who buy bread are also very likely to buy tomatoes, which you can then maybe make bread more expensive or tomatoes in discount. The other way around, I guess. So that's the frequent patterns and the association rules. That's the first step of pattern mining. But often we don't really have the sets that the order doesn't matter, right? We have things that happen in time and they happen after each other. So we go to our sequential pattern mining. For this we define our new database, a little bit of syntax I will explain. The less than and greater than signs you can ignore for now. They're just nice to have if you want to list them afterwards. But the thing you have to look at now is the parentheses. These things, this means that A, B, and C happen at the same time in this first example. But they do happen after A. And AC happens after A, B, and C, but AC again happen at the same time. So think again like a supermarket. I have my shopping basket. This is all at the same time, but the next time I come back, it's a new event. And from this, we can also again mine the frequent patterns, but this is actually much harder because we have this time element. And for Spark, prefix span is implemented for this algorithm. And Jelte will again tell you about this later. First, some real-world examples, like where is this being used, this pattern mining. And I guess nowadays a lot of things are used in combination, but some things that boil down to pattern mining and association rules are, for example, query recommendation. Like people who search for Yahoo also search for Yahoo Mail or Yahoo Calendar, or maybe the order, the sequence of Yahoo Mail is very likely, so you can already predict this word is being typed. And quite popular lately as well, I think, at least what I've heard, is the process mining area. Well, this is actually just maybe a specific use case of sequence mining, pattern mining, but like really focused towards processes. For example, applying some report at some company, and this is step one, and then there's another step where somebody looks at it, and there's another step where somebody gives it back, and etc. And you can look for patterns in this process and maybe find the bottlenecks or frequent patterns that happen all the time and optimize it in that way. It's also what sequence mining is used a lot for. And then we get the recommender systems, which we all know, like Amazon and Netflix and Bol.com and Spotify, like all based on, if you like this, you might also like this, which is quite easy to do with association rules. Of course, this is also combined with a lot of other data, like your age group or whatever, but you can also actually input this into your more complex pattern mining algorithms. But yeah, this is basically association rules, I would say. If everybody would like to disagree, this is the moment, because I will pass on the mic to Jelte. I guess not.
Thank you. Yeah, so Rutger already told some theory now, and I'll look into the Spark algorithms. So for this, we looked into the Scala code. Now, I'm a data scientist, so not a Scala programmer. So please be gentle there, but I think we got the right conclusions. So first of all, small outline of the prefix span algorithm. How does it work? So you have all your transactional database with sequences. First, for each of these sequences, you look for frequent single items. And actually, the algorithm is quite simple because it's only a 4-step process that we keep repeating. So find frequent single items. Next, we filter the database to only keep the sequences that actually have the frequent items. So for example, if A were frequent, we only make a database with only the sequences in which A occurred. And then we split those sequences into what is called a prefix and a postfix. So the prefix is basically the potential pattern, which is now only A. And the postfix is basically whatever remains after I find the point where A starts in the sequence. And then I repeat on this projected database. So this is probably, I don't think many of you already understood this way. So we have a picture, which usually helps. So yeah, looking again. First I look for frequent single items. And I find with a min support of 2, that G isn't frequent, so I'm gonna cross that one out. So now I have my prefixes for the next round. I can divide my search space. So for each prefix, I look at my transactions. I find the ones where the prefix occurs, and then I collect all the postfixes and put them in the projected databases. So if you look here, I circled the D step, or actually someone else did because we used the slides. So here you've got the deprojected database, and now I just start over. So again, I will count in the postfixes database, in the projected database, for frequent singletons. I'll check those out, see if those are frequent again, etc. And this is how you can mine your sequences. So that's the prefix span algorithm. So now the Spark FPM module. Maybe a quick show of hands. How many of you used this module once, or at least once? Okay, so I see 4 fingers. That's quite nice, quite nice. Okay, so we see a few parameters for the prefix span algorithm. First of all, the min support. So that's basically, say, a threshold on how often a pattern should occur in your database. The second one is the max pattern length. So because I just keep expanding and making them larger, I can stop early if I want to, and I'm only interested in patterns of a certain max length. The final thing is the max local projected database size. And this is basically when to stop distributing the computations and start doing things local. And we'll see more of this now. So yeah, this is basically an outline of the Scala functions that make up the algorithm. So first look for frequent items of length 1. Then they have one optimization that is removing the unfrequent items from the input sequences. So for each sequence I'm going to filter out the ones that I already know are infrequent. So I have to check fewer items basically. Next I'm going to do persist. So basically say whatever I can fit in memory, and the rest of it, the remainder, write it to disk. So now the actual mining. Basically I'm going to count which items occur frequently in the postfixes, so again the counting. Now I'm going to project again to find projected databases. And now I'm going to check, and as long as the database, the projected database, is smaller than the parameter I gave in, I'm going to do this in the RDD API. So basically with distributed code. And as soon as I can fit it in memory, I'm going to switch to local and just do a basic Scala implementation of the algorithm. So that's basically the way that this algorithm is implemented in Scala. So now we have a small Python demo. I think Rutger will do some notebooking. Yeah, let's start with this one. Yeah, so can you make it a bit larger? This is Command plus. Yeah, what's Command? Not a Mac guy. Larger, larger. Okay, so first of all, I'm going to do some imports, and I start my Spark process. Then I define some data, which are sequential patterns. I put them in an RDD. Now I'm going to train my prefix span model. Let's do a min support of 0.5. And boom, there they are. Frequent patterns. So it's quite easy, as you see, to use. And I think we have another demo, which is the FP growth. So that's an algorithm implemented for just the ordinary frequent pattern mining. So again, some item sets, and it's pretty much the same. So these are my item sets. Fit. And basically also, oh yeah, it's good to say that this one is quite new. It actually shipped with 2.2. I mean, at first it was in the MLlib only, and now it's in the ML library. So these are our frequent item sets, and we can also find the association rules. Yeah, it's magical. So that's just a single API show, basically. Now we also did something else. So I was looking, still a data scientist, so I want to apply things. So I was looking for a more interesting example, basically, of this pattern mining algorithm. So here I have a data set of all the lyrics of popular songs. So here, as you can see, there's a song, there's the artist, I have a URL, and basically I have all the text, so the complete lyrics. So 57,000 songs in here. Okay, so what am I going to do? I'm going to import the stop words list from NLTK. Who knows NLTK? Yeah, okay, there's quite a few more people. I do some pre-processing on my data set. So imported in pandas here. I'm going to lower all the words to don't have duplicates with that are the start of a sentence or with a capital letter. Split them up. I'm going to filter out the stop words. And I'm going to wrap them in a list because they're all separate item sets. Okay, so let's load them up. Min support of 0.05, because that's a bit more realistic for real applications. I'm going to find my my frequent sequences. Yeah, that's actually an important point. So only the ones that are longer than three item sets. So what we should get out now, basically I have all these songs. I'm looking for frequent patterns in them, frequent sequences in the lyrics. So basically these frequent sequences are sort of the universal patterns that occur in many songs. So basically now we should get the building blocks of universal song. It's making sounds, Rutger tells me, so that's a good sign with the Mac. A lot of blowing. Here we go. So these are the most frequent elements in popular songs. And of course that's cool. So basically if I have all of these, well, they're basically what, let's look in here. No, I'm, love, 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 love. I'm, don't I'm. Like, I'm like. So there's cool stuff in there. It almost looks like poetry or maybe even a song. Could it be a song? Rutger, what do you think? Rutger thinks it could be a song, so let's take a look. Maybe some background music. It's beautiful. Let's just listen a bit more. Yeah, that would be nice. Yeah, so that's another thing. It's really hard to stop. It wants to go to the end. Let's see what I can do. No, so we're just gonna let it keep playing. Oh, we do have control over the piano, so that's good. Yeah, so that was the Python demo, and of course this is fun stuff. But this is only the beginning of pattern mining. So a few more things that have never been implemented, or only by a few special minds, but we can't find them on the internet. High utility pattern mining. Basically, you could assign a value to each item and then only mine if the entire item set has some value larger than some amount. So, for example, here maybe I want to find interesting, again, maybe basket item analysis. So, transactions that people bought that were more expensive than so and so because my marketing budget is only so large. That's one thing you can do. A few more things we have. Sequence prediction. So this one's actually, yeah, I have a sequence of things that happen. Now, what's next in the sequence? What's going to come up? So this is actually a more popular problem, of course. Also in the space of recurrent neural nets, etc. these days. But still, if you need a simple algorithm, for example, a Markov chain could also implement this. Multi-dimensional sequential pattern mining. Basically, again, so sequential pattern mining, but now I can give some sort of context. So, for example, I know which group a customer is in, and I assign this as a sort of a tag. And now I can find different patterns, such as business customers in Boston of middle age, and they did BDCBA, that kind of thing. Last thing is pattern themes. So usually you look for interesting patterns on their own. But you could also say, maybe I want a group of patterns that describes my data set in a minimal way. So it's actually what you see here. So you have a code book, and each pattern, or in the data set, you can give a certain code. And now what's the minimum code length I can find to describe this data set? So it's kind of a compression way, and you hope you get out interesting patterns. I think this is it, actually. Yeah. Yeah. Yeah, so the same word can occur multiple times in a sequence, of course, and can still be a pattern. Yeah. So we take this entire song. That's one row in my sequence database. So if, for example, you get love, 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 and it occurs 4 times in the song, you can count it for your support. No, not the same item. No, so it should be sequential. So yeah. So, for example, maybe if you have a chorus that says love a few times, it's it's easy to get there. Or don't. Or any song with the chorus. Yes.
Some more pre-processing and just take one chorus, I guess. Maybe go line by line even if you want to.
Yeah, so that's a modeling thing you could do here. So instead of one sequence being the entire text of the entire lyrics, you can also say one sequence is maybe one row in your database. It's also possible. But yeah, we hacked this together in 2 hours. So other questions? Oh.
Are you planning to add new algorithms to Spark algorithm?
Yeah. So this guy has a PhD in pattern mining, I happen to know. So if you implement those, I'll gladly review, I think. Yeah, maybe not. Let's do it sometime on a Friday.
2 hours?
What's that? 2 hours? Not so sure. So that should be in Scala, and it was actually quite a lot of code, quite a lot of Scala code. Yeah.
What if you remove so many
for example, if we have the sentence I'm in love and to remove in, then well, it becomes harder to match it actually.
Yeah, it's a good question. Actually, the answer is that the first time I ran it, I found A, D, 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 A, D. So those were the patterns, were only D and A in there. And I thought, well, maybe let's remove the stop words. But I think if you model it as one row being a sentence in a lyric, then it makes more sense to keep all the words. Yeah.
The patterns you look at in your shopping example, you only look at things like a single event, a single purchase of several items. You also look at patterns that go over time. So if someone goes to the same shop 4 or 5 times a week and see if there are repeats in there or something like that.
Yeah, so this is one of the multi-dimensional ways. Then you, instead of saying having the Boston tag, you can, for example, add a timestamp. So that's maybe the number of the visit, for example, and then you can also find the sequential things. Maybe Rutger wants to add something to this.
I might have misunderstood the question a little, but aren't you just asking for the sequential pattern mining in itself? Like you combine the items bought at one moment to into one item set?
And then look at purchases that are done afterwards and see if there are patterns that repeat and see if there are.
Yeah, that's the prefix span algorithm Jelte explained, I think. Right? So that's actually just the prefix span which is available in Spark. So you can do that. Yes. Again, I could refer to the PhD sitting right there. He actually did something on this. So what? Just to explain a little, you could use these pattern teams to encode the database and then see which sequence of items doesn't fit with the pattern teams you found. So yeah, but that's more difficult. Usually you would just lower your support, but then you would start to find a lot of combinations and it will get really slow and not useful. So that is a problem, yeah.
Let's thank the speakers. So this was these were the presentations for today. We can have a drink still at the bar, and we close 9:30. So enjoy the rest of the evening. Thank you, guys.